Hi, so in my previous videos, you probably heard me talk about logic gates, and I even showed you some symbols of them, but I haven't properly explained how they work, well, at least not the kind I use, which is CMOS, but we're gonna get to that later. Now I just want to explain how do they work, and yeah, what are logic gates? So basically logic gates are, as the name implies, gates made out of transistors. You can either have CMOS or TTL, which is, or some other type of logic family, which means, but I use CMOS because that's complementary metal oxide semiconductor, which compared to TTL doesn't use BJT transistors, but it uses MOSFETs. I'm not gonna go into details about what MOSFETs are. You'll just have to believe me how they work for now, and I'll probably make a video at them at some point. So CMOS logic uses MOSFETs, two types of MOSFETs, N-channel and P-channel. You can see them here. Um, so N-channel MOSFETs are a type of a transistor which, when there is voltage applied to the gate, which is this pin number 3, the transistor acts like a short circuit. And when there is no voltage or ground voltage applied to pin 3 of this transistor, out, uh, the transistor basically acts like an open circuit, so there is no current flowing through and there is no voltage. And the P-channel MOSFET works in the exactly opposite way. So when the pin number 3 is high, the transistor is an open circuit, and when the pin 3 is low, that means the transistor is a short circuit. Well, not entirely, because these transistors have a resistance, but I'm gonna get to that now. The resistance with a smaller VGS gate source voltage, which I'm using, so they have a resistance, but I'm really not gonna get to that now, so we can just, for all intents and purposes, see that as though they were an open circuit or a short circuit. So yeah, now that we got that explained, I can probably get in what these gates are. So I have three main general logic gates: a NOT gate, an AND gate, and a NOR gate. I am gonna go one by one and explain how they work, and then we're gonna look at other types of logic gates. But these three are the main. Well, you can basically build an entire computer out of NAND gates, and NOR gates are just yeah, as you can see, the P channel and N channel is just swapped, so they use the equal amount of transistors. But yeah, let's first go into a NOT gate. So the NOT gate basically uh, inverts the output. So when A is high, the Q is low, and when A is low, Q is high. So how does that work? So when you have a high input on A, that means this P-channel MOSFET's gate is acting like a short circuit, which means these 5 volts are going to go over here, and this transistor is basically like an open circuit. So when this is low, there is 5 volts. Well, yeah, 5 volts is what I'm using, but you might have a higher voltage gate or something, but that's not really important now. The important thing is that you have 5 volts on this output, and the path to ground is closed. Well, it's open, but when you put a high state on this input, that means this P-channel MOSFET is not gonna be conducting anymore, and this N-channel MOSFET is gonna be basically connected to ground, which means there is gonna be low on this. So yeah, that's how a NOT gate work. So when you have this high, this is conducting like this, which means this is gonna be connected to ground, which means this is low because it's on ground voltage. And when this is low, this means this is conducting, which means there is a path from 5 volts power supply to to Q, which means this is high, and then this is acting like an open circuit, so this is low, and there is no path to ground. Yeah, you can see how this can be sort of an issue since you are shorting to ground or from 5 volts. So that's what that's taken care of what I said, because I use 20 volt circuits which operate at 20 volts max. So when there is a 5 volt difference on gate and source, which is this pin 1, this is source, and this is gate, this pin 3, that means there is like 2.5 milliamperes max going through the circuit, so it's safe to drive an LED with it or something. Yeah, basically the same thing happens over here, but this is a NAND gate, which means this is not AND. I'll explain what that means later, but you'll just have to know that you have to basically put both. By the way, these A pins and these B pins are connected together, but since it would be too confusing to connect them on the sheet, I just wrote it like this. I hope it's not too confusing. But when you turn the B, for example, high, and so does this B turn high, which means this P-channel MOSFET will stop conducting and this N-channel MOSFET will start conducting. But since there is no path, since this is low, there is no path through here, this is basically useless, and since there is one path from 5 volts over here, this doesn't matter. You have to turn both of these on high, which means it will disconnect from 5 volts and it will short it to ground like this, and basically it will then be low. And yeah, that's the only state it can be low, is when you basically turn both of these high. When you turn A and B high, the Q is gonna be low. And so yeah, that's when. And when you turn when there is only one turned high or both of them are low, the Q is gonna be high. And yeah, I'm gonna explain why that is in a second. Well, not why that is, but I'm gonna give you a table in a short moment. But we'll have to get to a NOR gate as well. So yeah, a NOR gate is basically a NAND gate, but it works a bit differently, which means when you turn A or B high, you'll cut off the path from 5 volts to Q, which means the Q will turn to low. If you select A, either A or B low, and then the path to ground will turn on. But so yeah, you'll have to turn at least one of these high in order for output to be low. If you turn both of them, it doesn't matter. At least one has to be high in order for Q to be low. Well, so I have prepared a little circuit over here, which is gonna be demonstrating how this actually works. So yeah, wait, give me a second, I'll just have to power it up. So you can find those transistors in a neat little package like this IC, like these ICs. Well, I'm gonna get into these two in a minute as well. So yeah, here is the NOT gate, which basically works like this. So you see, when there is a low input, well, basically 0 on A, the output, the Q, is gonna be high or 1. When there is 1 or high on the input A, the output Q is gonna be low. So I've basically done that over here. Yeah, you can see that it is actually like the IC 4069, which is this IC, a CMOS NOT gate. And as you can see, there is a green LED going through a switch, through a resistor to ground, so there is some voltage on the input, and then the output is going through this orange LED. I don't know if you can see it properly. yeah, through this orange LED to ground, which means you have something like this. Yeah, as you can see, here is the green LED, here is the orange LED, and here is the resistor under the LED. Yeah, well, yeah, there's the resistor. Okay, so when I turn the output high, as you can see, the input turns low. So yeah, that's basically what it does. So this is the circuit, how it actually looks. So now, yeah, I said I'm gonna be getting into this situation, which I've done over here, which means, yeah, I basically burned out the only NAND gate circuit I have, the only NAND gate IC I have. So I had to have a little ingenuity over here. So I connected an AND gate to a NOT gate like this, which means, yeah, it is basically inverting the input of an AND gate to match the outputs of a NAND gate. Basically, NAND gate means not AND. So yeah, this is actually correct. And as you can see, there are two push switches, two green LEDs, and one orange LED. And yeah, as you can see, there are two push switches. There are two green LEDs, two push switches, two resistors. By the way, these 3300 ohm, no, this 330 ohm resistors are not what you would typically want to use as a pull down resistor, as I use them over here, but since this is only for demonstration purposes and I need these LEDs to actually glow, I don't really mind using them because I'm not gonna be applying the circuit anywhere else. So I guess this is good for the application. And yeah, as you can see, when I turn on output, well, I should probably show you the table, the truth table. So yeah, this is a NAND gate. As you can see, this NOT gate turned into this little bubble over here because it has this bubble here. So it basically connected over here. And as you can see, when both of the inputs are low, the output is going to be low as well. When one of the inputs is high, the output is going to be still high. When one of the inputs, well, basically when both of these inputs are high, then the output is going to be low. Yeah, that's what basically a NAND gate is, and I'm probably gonna make a video on NAND gate logic soon. Well, not soon, but I'm gonna try and do it at some point to show you that you can build any other logic gate out of NAND gates. That's why NAND gates are generally considered general purpose gates. Yeah. So, and then as you can see, when I turn this on, nothing happens. When I turn this on, nothing happens. And when I turn both of them on, this one turns off. So it works as it should. Though you would probably want to use a single chip, not two chips like I did. You would probably want to use a 4011 chip, but I have used 4080, 4081 and 4069 chips to basically simulate an AND gate. So now there is the third gate, which is a NOR gate. I'm gonna show it to you. So yeah, this is the NOR gate, and as you can see, there is two green LEDs like usual, two push buttons, two resistors, NOR gate, and an orange LED, which, yeah, as you can see, it's like this over here. And when I press down one of those, well, I should probably show you the truth table first. So yeah, this is a NOR gate. As you can see, this matches as well. This is a NOT OR. I'm gonna show you an OR gate later. But as you can see, when it's only high when one of the inputs is when both of the inputs are low. Any other time it's just low. So yeah, as you can see, it's now high because both of these inputs are low, as you can see on the LEDs. But when I'll also you can see that there is the little bubble at the end as well. So now, as you can see, when I press only one of them, the gate will basically turn off. Yeah, the button is a little faulty, so yeah, you could see some blinking over there, but it's not the gate's fault, it's the button's fault. Yeah, so as you can see, you can turn it with any button off. So yeah, that's it for the general gates. And yeah, let's get into other gates. By the way, there are 7 types of gates. Can you please focus? Thanks. There are 7 types of gates, and there is another circuit I've prepared, and I'm gonna take it out. Wait. Yeah. Excuse me. So here is the circuit, and yeah, as you can see, there is a DIP switch, which means dual input package switch, um, which is this one. Yeah, and I have connected these pin numbers to inputs of the gate over here. Yeah, so as you can see, this is an AND gate, this is an OR gate, this is an XOR gate, and this is an XNOR gate. So let's start with an AND gate. So yeah, don't mind this one glowing LED, I'll explain it shortly. So the AND gate is this one, you've seen it probably before. And what does this one do is that basically when you have both of the inputs on, then the output is on as well, which means when A and B is high, the output is high as well. Yeah, this is how an AND gate looks. Here is probably drawn better. So yeah, as you can see, this has the similar configuration. There is the 330 ohm resistor, the orange LED as an output, the green LEDs, and the dip switch as an input. So yeah, there are these two, pin 1 and 2 are the inputs into the AND gate, and when we turn it on, when we turn one on, nothing happens. Wait. When we turn the other one on, nothing happens as well. Only when we turn both of them on, yeah, then the output turns on. Yeah, the chip might be faulty, but nope, or the wire was loose. Yeah, that's happens sometimes. But yeah, as you can see, when A and B are on, only then the gate is on. Yeah, that's nice. So another gate is an OR gate, which has a truth table like this, which, as you can see, when A or B is turned on, or both of them, doesn't matter, is turned on, the output is turned on as well, is high as well. So yeah, let's look at it on our circuit. It is the third pin, yeah, and the fourth pin, as you can see over here. Pin number 3 and 4 go into pins 1 and 2 of this chip. So when I turn on the pin number 3, yeah, as you can see, the output is turned on, is high. Yeah, and when I turn on the other one, doesn't matter. When I turn this one on, doesn't matter. Both of them are turned on. So yeah. So there is a third gate, which is an XOR gate. This one's a little complicated. Maybe it sounds like that. It's not actually, but maybe it sounds like maybe it sounds complicated since the name is not usual. But it's actually very logical, since we are dealing with logic gates. But it's very logical since, yeah, it's an exclusive OR gate, which means when only one is turned on, then the output is high. When both of them are high, the output is low. Yeah, well, that's why it's called exclusive OR, because you are gonna have one or another, but not both of them. This one has actually a wider range of applications, such as inverting, control inverting, or for example, if you want to check if like two numbers are different, not the same, because as you can see, when they are the same, the two inputs are same, 1 and 0 and 0, the output is low. When they are different, the output is high. So yeah, maybe that's what you can use an XOR gate for. It has actually a lot of uses, and it's a really useful gate, though it sounds very unusual. So the circuit over here is these two, pin 5 and pin 6, are connected over here to the XOR gate input, which, as you can see, is over here. So when I turn one, as you can see, it is default by low on low. Yeah, as you can see, when I turn it on, it turns on, but when I turn on the second one, it turns off. But when I turn on this, turn off this one turns on. So yeah, as you can see, the only one of them can be on in order to for an output to be high, which is very convenient for some uses, as I said before. And yeah, there is the fourth one, which is an XOR gate, which is XNOR gate, I'm sorry, which is this one, which is basically an inverted XOR gate. When we compare them, when we compare the outputs, it is inverted. As you can see, when this is 0, this is 1, this is 1, this is 0, yeah, this is 1, this is 0, this is 1, this is 0, this is 1. So yeah, it is basically an inverted XOR gate, and you can see it in the name, exclusive NOR gate, but this is exclusive OR gate. So yeah, basically, if we look at the truth table, we can see that this one actually says when you compare something, yeah, so when both of them are low or high, so when the outputs are equal, 0 or 1, then the output is 1. Yeah, that's what this can be, for example, used for comparing two numbers. So when we take a look at our circuit, these two last pins, 7 and 8, connect to these gate inputs, 1 and 2, through the resistors, as usual. You know the drill. So when I turn on 7, as you can see, this is on because the inputs are equal. They are both 0, so this is 1. When I turn this on, as you can see, this one is now 0, and this one is 1. This one is turned off, and this because these two are not equal. When I turn the second one on, as you can see, they are equal now. They are both high, so this one is high as well. But when I turn this off, they are not equal anymore, so this one turns off. So yeah, that's basically for the 7 basic types of logic gates. Don't worry if you don't understand the truth tables by now, because yeah, you'll learn them if you'll work with them for long enough. So yeah, you'll probably learn them. But there is actually an 8th logic gate, which I did not talk about, and which I'll probably not talk about in the detail, and which I don't have a paper for, which is a buffer. As you can see, it looks very similar to the NOT gate. Yeah, as you can see, the buffer is a triangle. The NOT gate is a triangle with this little bubble over here, which means its output is inverted. As you can see over here, the buffer basically passes on whatever there is through it. So if there is a 0 on the input, there is a 0 on the output. If there is a 1 on the input, there is a 1 on the output. You might ask, what is this used for? Well, the magic of CMOS circuits is that they don't draw any, well, they draw a little amount of current on these transistors, because these transistors, through their gate, there is nothing passing through them. So when you basically send like 5 volts at 2.5 milliamps, which can drive something like one LED to glow, as you can see over here, right? But if I were to connect the second LED, the IC wouldn't be able to take it. So these buffers are made to basically handle larger currents at the same voltage, which means though you basically just like pass the input on the output on A to Q, the the input is, if it's 2.5 milliamps max, this can probably draw like a 200 milliamps through it. So this means if you have the max of 2.5 milliamps, you can amplify it, let's say it like that, you can amplify it to 200 milliamps, which can be used, for example, if you want to drive a lot of LEDs, like an LED string or something like that, or a lot of parallel LEDs, or some higher power applications than a simple IC can hold. Yeah, it's basically a driver. Well, you can use it in a driver. It's not a driver in on itself, but you can use it in a driver, for example. So yeah, that's probably what a buffer is used for. I did not talk about it since it's not really a logic gate, since these other gates have a logic, like if both of them are on, or if at least one is on, or if only one is on, or yeah, if one is on, if the input is on, the output is off, but the buffer doesn't really have a logic, because it's like if A is on, B is on as well. So it's not really a logic gate. Well, at least I wouldn't say that it is, but it probably is, and I'm just making a fool of myself now. So yeah, that's about it on logic gates. You can use them basically to make a computer or something like that. They are actually used in computers. Well, you can probably say that computers are made out of them, since yeah, computers require logic to work. So yeah, these gates are basically circuits of transistors that create a computer, and they are really useful. I probably showed you a way in my previous videos how you can, for example, make a register out of them to store information, which uses NOR gates and some AND gates. So yeah, that's very useful. You can also, I forgot to mention that there is one really useful way to have a buffer, which is basically a tri-state buffer, which you can use to cut out a something out of a circuit, because as you can see over here, when there is something low, you basically short it to ground through Q, which you do not really want to do. So yeah, that's why we might want to use a buffer, for it not to be shorted to Q, but for it to be cut off from a circuit. I'll probably explore this concept in another video. So yeah, that's about it on logic gates. I hope you enjoyed the video. So yeah, see ya.